Let us now study the displacement method to obtain focal length of a convex lens. This displacement method is an experimental setup using which we can experimentally calculate the focal length of a convex lens. Here you can see a realistic setup on optical bench for experiment of displacement method. Here we are given an object and a screen placed at a distance d, and in between a convex lens is placed. And as we know, to obtain a real image on a screen, the separation d must be greater than 4 times the focal length of the lens. So here if a lens is displaced and placed at a position where a sharp image is obtained on a screen, and here we can see if object distance from lens is u and image distance is v in magnitude, then here we can directly write the separation between object and a screen is this d, we can directly write as u plus v, and in this situation the magnification produced for the image m1 is given as v by u. Now as we know in lens formula, reversibility of light is equally valid, so as image is obtained at a distance v when object is placed at a distance u, if the lens is displaced to another position such that now object is located at a distance v and image is produced at a distance u, or the separation between a screen and lens is u, then also image will be produced. So we can state in another situation d will remain u by v, and in second case the magnification produced for the sharp image will be u by v. And we can see in both the cases, or the lens position L1 or L2, if sharp images are being produced, then the product of their magnifications must be equals to unity. And here we can see the size of image 1 which was produced when lens was in position L1. If it was SI1, this can be written as M1 multiplied by size of object. And if we calculate size of image 2, which is the image size when lens is in position 2, then size of image 2 is M2 multiplied by size of object. So from these two relations we can see that size of object is equals to the geometric mean of size of image 1 and size of image 2. You must always keep it in mind. This is also quite useful whenever you are required to calculate the size of object by measurement of image sizes. Now another point which we can see here is if a lens displacement is taken to be x, then here displacement of a lens between its two positions over sharp images are obtained. This we can write as x, and here numerically it will be equals to v minus u. And directly numerically focal length of lens can be given as f is equals to uv upon u plus v, which can be further numerically expanded as u plus v whole square minus u minus v whole square divided by 4 times uv. That simplification you all know, but this will be 4 times u plus v. Simplification I have done it to express the focal length in terms of x and d, which is the separation between the lens positions and separation between object and a screen. So here the focal length can be directly given as d square minus x square by 4 times d. This is the expression using which experimentally we can find out the focal length of the lens, provided here the value of d must be greater than 4f. Here if d is equal to 4f, there will only be one position of lens which is exactly midway between object and a screen, for which a single sharp image can be obtained, but in that case the value of x will be 0.